Regardless of the speed with which they themselves are moving, all observers measure the same speed of light. To an observer on a platform, for example, this train's passing at a good clip. But to someone on the train's speed seems to be zero, and the ground outside seems to be moving instead. Therefore, as Galileo was well aware in the Renaissance, and as this fellow knows today, the speed of an object depends on the observer's speed. Consider two observers in relative motion. In this case, Albert and Henry, just for the sake of argument. At the exact place and time they pass each other, they observe a flash of light. A sphere of light expands outward from that point. Since each measures the speed of light relative to himself, each believes correctly that he is always at the center of that expanding sphere, even though they themselves move farther and farther apart. How can two people in different places both be at the center of the same sphere? To confirm his perception, each sets up light detectors an equal distance apart. However, while Albert's detectors register the light arriving simultaneously, he believes the light strikes Henry's detectors at two different times. Meanwhile, Henry sees the same thing in reverse. They agree on the speed of light, but they disagree on whether events happen simultaneously or at different times. This is not semantics, nor a petty debate. It means that time, as well as distance, has to be affected by motion. 1905, Bern, Switzerland. Einstein, a young physics student supporting himself as a patent clerk, finds himself disturbed by seeming inconsistencies at the very core of physics. He sets forth two fundamental postulates. The first is Poincaré's relativity principle. The laws of physics are the same for all inertial frames. His second postulate states that the speed of light is the same for all observers. He simply assumes the phenomenon that Lorentz has been struggling to explain. From these two postulates alone, Einstein deduces exactly the same equations Lorentz discovered earlier. But now they have a very different meaning. The fundamental concepts of space and time have become intertwined. The essence of the idea can be understood by visualizing time as if it were another dimension. Albert, standing still in space, flows through time, so that a vertical line represents a fixed point, x equals 0, in his reference frame at different times, while a horizontal cross-section represents simultaneous times in different places. On the other hand, someone in motion, Galileo for example, traces an oblique path. So while what Albert thinks of as a fixed point makes a vertical line, Galileo's idea of nothing happening appears as a tilted line at x prime equals 0, or anywhere else in his frame. But of course, If Galileo had drawn the picture, his line for standing still would be vertical, and Albert's would be tilted backward. The same idea can be used to show the relativity of time. When Henry and Albert observed the same expanding light sphere, it reaches their detectors at definite points in time and space. These are called events. Meanwhile, the light itself traces out a cone. To Albert, events on the horizontal cross-section are simultaneous. For him, one of Henry's detectors flashes first. Then both of his own flash simultaneously. And finally, Henry's other detector flashes. So he thinks these two events are simultaneous. But Henry thinks these two events are simultaneous. So not only are Henry's lines of constant position tilted, but so are his lines of simultaneous time. For Henry, simultaneous events take place everywhere on a tilted cross-section. So he thinks one of Albert's signals goes first, then both of his, then Albert's other signal. Of course, if Henry were drawing the picture, he would draw his lines of constant place and constant time perpendicular to each other. Amazingly, that wouldn't change the light cone at all. This way of looking at things is called a space-time diagram, and many of the strange effects of relativity can be visualized this way. For example, Albert thinks that Henry's ruler isn't quite a meter long, while Henry, seeing Albert speed by, thinks Albert's ruler is shorter. On the space-time diagram, Albert measures lengths on his space axis, where Henry's ruler is shorter. But on Henry's axis, the situation is reversed, and Albert's ruler is shorter.
It's possible to say that Einstein made only minor contributions to the theory of relativity, just as it's possible to say that Copernicus did nothing but a trivial mathematical transformation of coordinates. But to say that ignores in the most profound possible way the real history of both of those subjects.